In this exercise, we are asked to write out the truth sets of these 5 predicates. Now, the truth set of a predicate is just the set of all things for which that predicate is true. So let's look at our first predicate, even num x, which stands for x is an even integer. So the truth set just consists of anything x that satisfies this statement, x is an even integer. So the truth set is just the set of even integers. And here's one way we can write that set. So here, this is the set of all numbers of the form 2x, where x is any integer. So all multiples of 2. Right. Next, we've got the predicate even prime x, which stands for x is an even prime number. Now, there is only one even prime number, and that is 2. So that is the only number for which this predicate is true. And so the truth set consists of just one element, 2. Next, we have deadly sin x, which stands for x is a deadly sin. So the truth set of this is just the set consisting of the 7 deadly sins. There it is, the 7 deadly sins. Next, we have a predicate sum of x, y, z, which stands for x, y, and z are integers, and x plus y equals z. So this predicate has 3 free variables, and so the truth set of this predicate will consist of elements which themselves consist of 3 values representing the 3 free variables. Each element of the truth set will be some triple x, y, z, such that x, y, and z are all integers and they satisfy this property. So we can write that out like this. So the truth set is the set of all triples of integers such that the first 2 add together to make this the third. Our final predicate is sum of u5v, where sum is as defined in D. Now notice that we've gone from x, y, z to u5v. 5 is not a free variable, while u and v are. So we've gone from having 3 free variables to just 2. And this means that in the truth set of this predicate, each element must only consist of 2 values, u and v, that are both integers and that satisfy u plus 5 equals v. So we can write this. And we have the truth set is exactly the set of pairs of integers that satisfy the first of the pair plus 5 equals the second of the pair. And we're done. In this exercise, we have a predicate defined on the set of students in your class, v of x, which stands for x visits their parents every weekend. Our task is to express these 4 quantifications in natural English. So let's look at A. Exists X such that V of X is true. So in English, this says that there is a student that visits their parents every weekend. B says for all X, V of X is true. So that says that every student visits their parents every weekend. C says there exists a unique X such that it is not the case that V of X is true. So in natural English, this says that there is only one student that does not visit their parents every weekend. And finally, for all X, it is not the case that V of X is true. So no student visits their parents every weekend, right? For all X, V of X is not true. So every student, it is not true that they visit their parents every weekend. No student visits their parents every weekend. And we're done. In this exercise, we consider two predicates defined over the set of all people. S of X stands for X is a sore loser, and L of XY stands for X likes Y. Our task is to express this statement, nobody likes a sore loser, in predicate logic using these two predicates. Now let's think about this statement and think about how else we could express this. Nobody likes a sore loser. We could say that there are no two people, X and Y, such that Y is a sore loser and X likes Y. Right? It is not the case that there are two people, X and Y, such that Y is a sore loser and X likes Y. And this is something we can express in predicate logic. So it is not the case that there exists a person X and a person Y such that Y is a sore loser and X likes Y. And there is our statement in predicate logic. In this exercise, we have defined three predicates and we want to translate some English statements into predicate logic. So let's take a look at the first statement. All bees like some flowers. So first of all, let's think about what it means to say X likes some flowers. So how can we rewrite this? Well, we can say that there is something Y, right? There is something Y such that Y is a flower and X likes Y, right? So there is Y, right? There is something Y taken from the universal discourse, which is just things, right? So there is a thing, Y, such that, and now we have two conditions, two predicates such that y is a flower, first of all, and x likes y, right? Now hopefully you see that these two statements are equivalent. X likes some flowers, and there is a y, there is some y, such that y is a flower, and x likes y. So let's translate this into predicate logic. So there is y, there is some y, exists y, such that y is a flower, well, we have that defined as a predicate, and x likes y, right? So this is how we write this statement, x likes some flowers. Okay, now let's take a look at the original statement. All bees like some flowers. Well, how can we rewrite this? Well, we can say that for anything x, right, for all things x, if x is a bee, then x likes some flowers. Yeah? Okay, let's write that. For anything x, if x is a bee, then x likes some flowers. And now we can try to translate this into predicate logic. So for any x, we know how to write that. And we now have an implication, right? If x is a bee, then x likes some flowers. So we'll have an implication here. B of x implies that x likes some flowers. Well, we've just seen how to write that, right? This statement says exactly that x likes some flowers. So let's write it in here. So this statement says, for anything x, if x is a bee, then there is something y such that y is a flower and x likes y. And that's our statement. Here's our second statement. No bee likes only flowers. Okay, so let's first think about what it means to say x likes only flowers. Think of it this way. So x likes only flowers. So if we take anything y, right, anything, we're calling it y, and we find that x likes this thing, y, then we can conclude that this thing y is a flower, because x likes only flowers. Yeah? So for anything y, if x likes y, then we can conclude that y is a flower. Yeah, because x likes only flowers. now we can translate this into predicate logic. So for any y, if x likes y, so we have a predicate for that. If x likes y, then y is a flower. So f of y. Okay, so this statement says that x likes only flowers. Now let's return to the statement up here. No b likes only flowers. So how can we rewrite this? Well, we can say that there is not a thing x such that x is a bee and x likes only flowers, right? So there does not exist such an x. Okay? There does not exist a thing x such that x is a bee and x likes only flowers, right? So let's translate this into predicate logic now, right? So to say that does not exist this x, right? You simply say not exist, right? So we have this meaning there exists some x. So negating it, we have it does not exist x such that b of x, right? X is a b, and x likes only flowers. Well, how do we write that? We've just written it here, yeah? So we can just copy this into our statement on the left. And there's our statement. Our third statement is no bee hates all flowers. So first of all, let's think about what it means to say x hates all flowers, right? Hates meaning does not like. All flowers. So, how can we rewrite this statement? X hates all flowers. So, we can say for anything y, right? If we take anything, call it y. If this thing y is a flower, then x hates it, right? X does not like it. So, for any y, if y is a flower, then x does not like y. And how can we write this in predicate logic? Well, it's quite easy to translate from here. Right? For any y, and we have an implication now. If y is a flower, then, so y is a flower, then x does not like y. So it is not the case that X likes Y. So this statement says that X hates all flowers, right? So now let's take a look at our statement up here. No bee hates all flowers. So how can we rewrite this? We can say that there is no thing X, right, such that X is a bee and X hates all flowers, okay? There does not exist X, right? There does not exist X such that X is a bee and X hates all flowers. And now we can translate this to predicate logic. So there does not exist X, right? It is not the case that there exists X such that X is a bee and X hates all flowers. We've just written here, this statement means X hates all flowers, so let's copy it. And there is our statement. Now that we have these three statements written in both English and in predicate logic, the final part of this exercise is to find the negation of the three statements. Again, both in English and in predicate logic. Okay, so let's take a look at the first statement. All bees like some flowers, which we found to be written like this. So, if it is not the case that all bees like some flowers, then it must be the case that some bees don't like any flowers, right? So the negation of the first statement, that all bees like some flowers, is some bees do not like any flowers. And here it is written in predicate logic, so there is some X such that X is a bee, and for any Y, if Y is a flower, then X does not like Y. Okay? The second statement, no bee likes only flowers, written like this in predicate logic. Well, if we negate that, so if it is not the case that no bee likes only flowers, then it must be the case that some bees like only flowers. Yeah? So the negation is some bees like only flowers, written there is some X such that X is a bee, and for all things Y, if X likes Y, then Y must be a flower. Right? Finally, no bee hates all flowers. Well, if we negate that, so it is not the case that no bee hates all flowers, then it is the case that some bees hate all flowers. Yeah? So some bees hate all flowers. There is some X such that X is a bee, and for all things Y, if Y is a flower, then X does not like Y. So there are our three statements negated. In this exercise, we're given a predicate T of SC, which represents the statement student S takes course C. Our task is to express these two statements in predicate logic. Firstly, Alice and Bob take all the same courses. Another way to say this is for anything X, Alice takes course X if and only if Bob takes course X. So they take exactly the same courses, right? So we start with the universal quantifier. For anything X, and now we say Alice takes course X if and only if Bob takes course X. And we use this operator. This is the equivalence operator. So Alice takes course X if and only if Bob takes course X. Our second statement is Alice and Bob do not take any courses together. Now, before we translate this, we should note that this is not the negation of our first statement. Okay? It's not the negation of that statement. In particular, both statements are false if Alice and Bob take one or more courses together, but not all courses together. Okay, now let's write the predicate logic. So we want to say Alice and Bob do not take any courses together. Another way to say this is there does not exist an X such that Alice takes course X and Bob takes course X. So we start by saying it is not the case that there exists some X such that Alice takes course X and Bob takes course X. And we're done. In this exercise, we're given three predicates defined over the set of all people. Welsh X stands for X is Welsh, Smart X stands for X is smart, and likes XY stands for X likes Y. Now our first task is to express these four statements in predicate logic. So let's start with no smart person likes Donald. Another way to say this, there does not exist a person, X say, such that X is smart and X likes Donald. No smart person likes Donald. There is no person that is both smart and likes Donald. There does not exist a person X such that X is smart and X likes Donald. The next statement is there are smart Welsh people. So there is some person, X, say, such that X is both smart and Welsh. There exists an X such that X is smart and X is Welsh. There are smart Welsh people. Next, smart people like Welsh people. Okay, let's think about how else we might say this. We could say that for any person X, say, if person X is smart, then for any person Y, if Y is Welsh, then X likes Y. Okay, so here's the start. For any person X, if X is smart, now we want to say X likes Welsh people. So we're going to say for any person Y, we use a different variable. If Y is Welsh, then X likes Y. And this says that smart people like Welsh people. Our last statement is Delyth isn't the only smart Welsh person. Now this is an interesting one. So this tells us that there is a smart Welsh person that is not Delyth. Now it's also heavily implied, and this is how we will interpret it, that Delyth is a smart Welsh person, right? Delyth is a smart Welsh person, and not only that, she isn't the only smart Welsh person. So there is another person that is smart and Welsh and is not Delyth. So we'll start our statement by saying that Delyth is smart and Delyth is Welsh. And now we want to say that there is a person that is smart and Welsh and is not Delyth. So there exists a person, X, such that X is smart and X is Welsh and X is not equal to Delyth. So there is another smart Welsh person other than Delyth. Let's look at our next task. Our last task is to translate this statement into English. So let's read it. This says, there exists an X such that X is Welsh, and for all Y, if X likes Y, then Y is smart. So there is a person that is Welsh. There are some Welsh people, and for any person Y, if the person likes Y, then Y is smart. So the only people that are liked by X are smart people. So there are some Welsh people that only like smart people. And we're done. In this exercise, we're given a predicate, L of xy, which represents the statement x loves y, where the universe of discourse is this set here. And our first task is to translate these three statements into predicate logic. So the first statement is, everyone loves the cat. So for any animal X, X loves the cat. cat here is not a free variable, so it doesn't need a quantifier, right? Cat is taken directly from the universe of discourse. So this says that for any animal X, X loves the cat. Everyone loves the cat. Secondly, no animal loves any animal. So there does not exist an animal, X, say, such that there exists an animal Y, such that X loves Y. Again, there is no animal X such that there is some animal Y that X loves. No animal loves any animal. And thirdly, some animals both love and are loved by the cat. So there is some animal, X, say, such that X loves the cat and the cat loves X. Our next task is to translate these two statements from predicate logic into natural English sentences. So firstly, let's try to read this statement. This says, it is not the case that there exists some X such that for all Y, X loves Y. So there is no animal X such that for all animals Y, X loves Y. Or there is no animal that loves every animal. No one loves everyone. Next, let's try to read this statement. For all X, there is some Y such that X loves Y and Y loves X. So for all animals X, there is some animal Y such that X both loves and is loved by Y. Or every animal both loves and is loved by some animal. Everyone both loves and is loved by someone. In this exercise, our task is to express these statements in predicate logic. Let's take a look at the first statement. Jane saw a bear and Roger saw one too. So the first thing to do is to define some predicates. Now I'm going to define two predicates. So we have bear X, which says that X is a bear, and saw XY says that X saw Y. And that's all we need for this statement. So what we want to say is that there is a bear that Jane saw, and there is a bear that Roger saw. There is something X, such that X is a bear and Jane saw X. That's the first part. Now we want to say that this is true, and there is a bear that Roger saw. So we need to write basically the same statement, but with Roger instead of Jane. So there is a thing Y. We've used Y instead of X. I could have used X again, since they are separate statements, but I've used Y to differentiate. There is something Y, such that Y is a bear, and Roger saw Y. Jane saw a bear, and Roger saw 1 too. Our second statement is Jane saw a bear and Roger saw it too. Now the difference here is that Roger saw the same bear as Jane. So we don't have two different bears. But other than that, it's pretty similar. So I'm going to use the same predicates, bear x and saw xy. And I want to say that there is something x such that x is a bear and Jane saw x and Roger saw x. There is something x such that x is a bear, Jane saw x, and Roger saw x. Let's look at a couple more statements. We have another two statements to look at. Firstly, if anyone can do it, Jones can. Now I'm going to define one predicate for this. I will let can do x stand for the statement x can do it. Now this is an if-then statement. If anyone can do it, then Jones can. And another way to say this is if there is a person that can do it, then Jones can do it. Again, it says if there is some x such that x can do it, then Jones can do it. If anyone can do it, Jones can. Our next statement is if Jones can do it, anyone can. Again, it's an if-then statement. If Jones can do it, then anyone can do it. This time we mean that if Jones can do it, then for any person, x say, x can do it. If Jones can do it, then for any person, x, x can do it. And we're done. In this exercise, our first task is to express these four statements in formal predicate logic, where we have the predicate f of xy defined to be the statement x can fool y. Right? Now, our first statement says everybody can fool Fred. Right? So we could say for any person x, x can fool Fred, right? Simple enough. So if we take any person x, then that person can fool Fred. Right. Now our second statement says everybody can fool somebody. Okay? So again, if we take any person x, then there is some person, say y, such that x can fool y. Right? So for any person x, there is a person y, such that x can fool y. Now our next statement says there is someone who can fool everyone. So this time we're saying there is some person x, such that for any person Y, X can fool Y, right? Notice that these two formulas look very similar, but they are very different, right? Changing the order of the quantifiers changes the meaning of the statement. Our final statement says, no one can be fooled by everyone. So we could say it is not the case that there is some person X such that for all people Y, Y can fool X. Right? So it is not the case that there is some person who can be fooled by everyone. Let's write this. So look again, it is not the case that there is some person X such that for all people Y, Y can fool X. Okay, let's move on. Our second task is to translate these two expressions into natural English sentences. So let's look at our first expression. It says, for all X, not f of xx. So what this is saying is, for any person X, it is not the case that X can fool themselves, right? So we might say, no one can fool themselves. Now our second statement is, exists X, exists Y, such that f of Nancy X and f of Nancy Y and X does not equal Y. So there exists a person X and a person Y such that Nancy can fool X and Nancy can fool Y, and X and Y are not the same person, right? X and Y are not equal. So there are two different people, X and Y, that Nancy can fool. Nancy can fool two different people. In this exercise, our task is to express these statements in predicate logic. Let's take a look at the first one. Anyone who has forgiven at least one person is a saint. Now the first thing we need to do is to define some atomic predicates. Now I'm going to define two predicates for this first statement. Saint X represents the statement X is a saint, and forgiven XY represents the statement X has forgiven Y. Okay, let's look at the statement again. Anyone who has forgiven at least one person is a saint. So we can say, for any person, X say, if there is a person Y, such that X has forgiven Y, then X is a saint. So for any person X, if there is a person that X has forgiven, then X is a saint. Again, for any person X, if there is a person Y such that X has forgiven Y, then X is a saint. Our next statement is, nobody studying computer science is smarter than everyone studying maths. For this one, I'm going to define 3 atomic predicates. Our predicates are CS, X, which represents X is studying computer science. Maths X represents X is studying maths. And smarter XY represents X is smarter than Y. Looking at the statement again, nobody studying computer science is smarter than everyone studying maths. Another way to say this is that there does not exist a person, X, say, such that X is studying computer science and X is smarter than everyone studying maths. So we start by saying there does not exist an X such that X is studying computer science and now we want to say that X is smarter than everyone studying maths. So we can express this by saying for any person Y, say, if Y is studying maths, then X is smarter than Y. There is no person that is studying computer science and is smarter than everyone studying maths. Let's look at a couple more statements. Our third statement is anyone who has bought a Rolls-Royce with cash must have a rich uncle. For this statement, I'm going to define 3 predicates. Rolls X stands for X has bought a Rolls-Royce with cash. Rich X stands for X is rich, and Uncle XY stands for X is the uncle of Y. Now, the statement again says anyone who has bought a Rolls-Royce with cash must have a rich uncle. So for any person X, say, if X has bought a Rolls-Royce with cash, then X has a rich uncle. So we'll start the statement with for any X, if Rolls X, then, and now we want to express the statement X has a rich uncle. One way we can say that is there is a person, Y, say, such that Y is rich and Y is the uncle of X. Making sure to get the variables in the right order in our predicate. Our final statement is everyone likes Mary except Mary herself. For this one, I will define just one predicate. Likes XY stands for X likes Y. Now we want to say that everyone likes Mary except Mary herself. So for any person X, say, if X is not Mary, then X likes Mary. For any person, if that person is not Mary, then the person likes Mary. But we're not done there. We need to add, this is true, and Mary does not like herself. and not likes Mary Mary. And we're done. In this exercise, we are expressing some English sentences in predicate logic. Okay, and we have to introduce our own predicates to do this. So let's take a look at this sentence. Time waits for no man. Okay. So thinking about how we might say this in other ways, we could say, there does not exist a man for which time waits. Okay, so there does not exist a man for which time waits. So thinking about the kind of predicates we might want to introduce, we'll definitely want one that expresses that something is a man, right? So something like this would do. Man of X expresses X is a man. Okay? So it does not exist a man for which time waits. So another predicate we might want to introduce is something expressing that X waits for Y. Yeah, that something waits for something else. So let's introduce that. Okay, so waits of X, Y expresses X waits for Y. Okay? Now we can try to write this sentence in predicate logic. So we want to say that there exists no man, so there does not exist a man for which time waits. So there does not exist some X such that X is a man and time waits for X. Okay? So it is not the case that there exists X such that X is a man and time, okay, so time is not a free variable, time is an element of the universe of discourse. So time waits for X. So this expresses our sentence. Our second sentence is this. We all live in a yellow submarine. So how might we express this differently? Well, we might say, for all things that are one of us, okay, so that would be the we all. For anything that is one of us, there is a yellow submarine that thing lives in. So let's introduce some predicates, right? So we want something to express that an object X is one of us, okay? So this predicate, one of us of X, expresses X is one of us. Okay. Now we need some predicates to describe that something is yellow, that something is a submarine, and that something lives in something else. Okay? So let's introduce those. So these predicates express X is yellow, right? That's yellow of X. Submarine of X expresses X is a submarine, and lives of X, Y expresses X lives in Y. Okay, so now we can try to write this sentence. So we all live in a yellow submarine. So we could think of this as, for anything X, if this thing X is one of us, then there is some other thing, Y, that is yellow, that is a submarine, and such that X lives in Y. Okay, so let's write this out. So for all X, if X is one of us, okay, so we want an implication here. If X is one of us, then X lives in a yellow submarine. So there is a yellow submarine, right? There is a thing Y, such that Y is yellow. And Y is a submarine. And X lives in Y. And there is our statement in full. So for anything that is one of us, there is a yellow submarine that thing lives in. Let's look at one more. Our third sentence is, every story has two sides. So how else might we say this? We could say that for anything, right, if that thing is a story, then there are two things, let's say A and B, that are both sides of that story. Okay? What kind of predicates might we need? Well, we definitely need something to express that X is a story. Yeah? So let's start with that. Okay. And we also want to express that something is a side of something else. Right? Because we want to say that a story has two sides. So there are two things such that both are a side of the story. So we need another predicate for this. So this predicate, side of xy, expresses that x is a side of y. Okay, now let's write our sentence. Every story has two sides. So for anything x, if x is a story, then there are two things, let's say A and B, such that A is a side of x and B is a side of x. Okay? Let's write that. So if we take anything x, and that thing happens to be a story, then, okay, there is a thing A and there is a thing B, right? There exists A and there exists B. Such that A is a side of X and B is a side of X. But we're not quite finished there, because right now we don't know that A and B have to be different things, okay? So A and B could be equal, but that would not express that the story has two sides, right? Then the story would still only have one side. So we need to express that A and B are distinct, right? So, and A is not equal to B. And there's our sentence. For all things X, if X is a story, then there are two things, A and B, such that A is a side of X, B is a side of X, and A and B are distinct. Our next sentence is a longer one. So let's read this carefully. You can fool some of the people all of the time, and all of the people some of the time, but you can't fool all of the people all of the time. Okay, so I'm going to introduce a predicate that expresses that X can be fooled at time Y. Okay? Now, notice that we're saying three things in this sentence, right? And it can be broken up nicely. So you can fool some of the people all of the time, and all of the people some of the time, and you can't fool all of the people all of the time. Okay? So there will be three segments connected with the AND operator. Okay? So let's look at the first segment. You can fool some of the people all of the time. Right, so let's write that. Now for some things X, there are some things X that can be fooled at all times Y. Okay? And, now looking at the second segment, you can fool all of the people some of the time. So for all things X, for all things X, there is some time at which X can be fooled. Okay? So there is some Y such that X can be fooled at time Y. And finally, our third segment, you can't fool all of the people all of the time. Okay? So it is not the case that for all people and all times, for all people X and all times Y, X can be fooled at time Y. Okay? So let's write that. It is not the case that for all X and for all Y, X can be fooled at time Y. And there is our whole statement. Let's look at one more. Our final sentence to translate is, there are infinitely many twin primes. Okay? And a twin prime means two numbers n and n plus 2, right? So a number that is 2 greater than n, and they are both prime. So that's what a twin prime is. And the sentence to translate is there are infinitely many such twin primes. Okay? So we'll start by introducing a predicate to express that x is a prime. Okay? So prime x expresses that x is prime. Now, let's express the statement y and y plus 2 are twin primes. Okay? So this can be expressed y is prime and y plus 2 is prime. Okay? So this statement expresses that y and y plus 2 are twin primes. Yeah? Now, how might we express that there are infinitely many such primes? Well, what does it mean for there to be infinitely many? So one way we could think about it is if you take any twin prime, you can always find one that's greater, right? You can always find a number that's greater than y that is also in a twin prime. Okay? And then that shows that the list goes on and on and on infinitely, right? Because if you think you found the last twin prime, no, there is one greater, right? At least one greater. And then you look at that one and you see there's another one greater still, right? So that really does show that there are infinitely many. If you say that for any such twin prime, there is one that is greater. Okay. So how about if we write this? So let's consider what's written here. Right, so for any x taken from the set of natural numbers, right? So for any natural number x, there is some natural number y, okay, taken from the set of natural numbers. So there is some natural number y such that y is greater than x and y is in a twin prime. Yeah? So we've expressed this statement here, that y and y plus 2 are twin primes. And we're also saying that y is greater than this natural number x. And since we're claiming that this is true for any natural number x, right, this means that if we have any twin prime, right, then that prime will be a natural number. So we can find another number that's greater than that, and that will be part of a twin prime. Okay, so this statement expresses that there are infinitely many twin primes. In this exercise, we assumed this predicate prime of x, expressing x is prime, right? But we might want to express this more explicitly, and we can do that using predicate logic. So let's think about what it means for x to be prime. Okay? Well, we know that any prime number is a natural number, and it's greater than 1, right? Because 1 is not prime, and its only factors are 1 and itself. Yeah, so that's what it means for a number to be prime. So in logical notation, this statement can be written x is a natural number and x is greater than 1 and this is the tricky bit. We want to express that x's only factors are 1 in itself, right? So if we factorize x as two numbers multiplied, right, then one of those numbers must be 1. Okay? So let's write it like this. For any natural number u, and any natural number v, if u times v is equal to x, then either u is equal to 1 or v is equal to 1. So this statement expresses that x is prime. In this exercise, we want to translate two expressions in predicate logic into English. Let's look at the first one. This says, for all x, man x, and for all y not married to xy implies not happy x. Okay, there's a lot to unpack here. First of all, this is a statement about all people x. So for any person x, and then we have an if-then statement. If something, then x is not happy. So let's now examine what is in the first part of this implication. This says x is a man, and for any person y, x is not married to y. So x is an unmarried man, is what is inside these parentheses. Putting that back into the whole statement, we get for any person x, if x is an unmarried man, then x is unhappy. So the statement says unmarried men are unhappy. Let's look at the second expression now. This says that there is some z such that z is a parent of x and z and y are siblings and y is a woman. Okay, so y is a woman and is the sibling of someone, z, that is the parent of x. In other words, y is an aunt of x. Now note that the first expression has no free variables. It is a proposition. It is true or false. All unmarried men are unhappy. The second expression, on the other hand, does have free variables. Y is the aunt of x. So it's not a proposition. We can't say that that is true or false. It is just a predicate. We want to express these three statements in predicate logic. First of all, at least three items have property P. Well, we can say that there exists some x, some y, and some z, such that x, y, and z all have property P. Here we use the predicate Px to say that x has property P. So this says that there exists some x such that there exists some y, such that there exists some z, such that x has property P, and y has property P, and z has property P. But this isn't quite enough to express that at least 3 items have property P, and that is because nothing here says that x, y, and z are necessarily different items. It could be that x and y are in fact exactly the same thing, or x and z, or maybe all 3 items are exactly the same thing. So this could in fact still mean that just 1 item has property P, or just 2 items. So we need to add something to this formula to say that x, y, and z are all different things. So we can do that just by adding and x and y are not equal, they are different things, and x and z are not equal, and y and z are not equal. This now says that at least 3 items have property P. And I'm going to call this formula L. And you'll see in a moment why I'm giving this formula a name. Let's move on to the next statement for now though, which is at most 3 items have property P. Now we can take inspiration from our first answer to get this one. At most 3 items have property P. Another way to say that is it is not the case that 4 or more items have property P. So it is not the case that at least 4 items have property P. To say that at least 4 items have property P is very similar to what we wrote here. This says at least 3 items have property P. So we need to write a very similar formula and just add another item. So that's exactly what I've done here. It's pretty much the same statement, just I've got another thing here. So there exists an x, a y, a z, a w, such that x, y, z, and w all have property P, and they're all different things. None of them are equal to each other. So without the negation, that says at least 4 items have property P. With the negation, it says that it is not the case that at least 4 items have property P, which is the same as saying that at most 3 items have property P. And we'll call this formula M. And our last statement is exactly 3 items have property P. So let's call this statement E. Now, to say that exactly 3 items have property P is exactly the same as saying that at least 3 items have property P and at most 3 items have property P. So it's just L and M. As simple as that. And we're done. In this exercise, we have 3 statements in English, and we want to express the negations of the 3 statements. At first, we will express them in English, and we'll then translate each statement and their negation into predicate logic in order to confirm that our answers are correct. Okay, so let's take a look at the first statement, A. There is someone in the class who does not have a good attitude. So the negation of that, right? So if it is not the case that there is someone in the class, then there is there is not anyone in the class who does not have a good attitude, or more naturally, we might say everyone in the class has a good attitude, right? Our second statement says, no man with long hair can fail to be a poet. So the negation of this would be, there is a man with long hair who is not a poet, right? So this man can fail to be a poet despite having long hair. And finally, our third statement says, everyone who has not been vaccinated got sick. So if this were not true, right, so the negation of this would be, there is someone who has not been vaccinated but did not get sick, right? So if it is not the case that everyone who has not been vaccinated got sick, then there must be someone who has not been vaccinated but did not get sick. So there is someone who has not been vaccinated but did not get sick. Now let's translate these statements and their negations into predicate logic. Here we have a statement, there is someone in the class who does not have a good attitude, and its negation, everyone in the class has a good attitude. Let's translate these into predicate logic. So, there is someone in the class who does not have a good attitude, right? So there is something X such that X is in the class and X does not have a good attitude. So using the predicates class and good to represent X is in the class and X has a good attitude, there is our statement written in predicate logic. So there is an X such that X is in the class and X does not have a good attitude. Okay, now let's translate the negation. Everyone in the class has a good attitude. So for any X, if X is in the class, then X has a good attitude, right? So for any X, right, and X is anything, right? So for any X, if X is in the class, okay, well then we know that X has a good attitude, right? Because everyone in the class has a good attitude. So class X implies that X has a good attitude. Okay? We have claimed that the negation of this statement is this second statement. Now we're going to show that this is in fact true, and we are going to use these established laws of logic. So let's first take a look at these laws. Law 1. Well, this statement says it is not the case that either P or Q are true. Well, then this means, of course, that they are both false, right? So not P is true and not Q is true. Second law states the first statement here says it is not the case that P and Q are both true. Well, yeah, this means that either P is not true or Q is not true. Right? Our third law, statement on the left, says it is not the case that there is some X for which P holds. Okay, well, if there is no such x, well, this means that for any x, P does not hold. Yeah? Similarly, law 4, statement on the left, says it is not the case that for every x, P holds. Well, this means that there must be some x for which P does not hold, and vice versa, right? Law 5 is probably the first law of logic that many of you have encountered, the law of double negation. So not P is equivalent to P. And finally, possibly the most interesting of the 6 laws we're using, P implies Q is equivalent to not P or Q. Now you can convince yourself of this by drawing truth tables for both of these formulas, but let's just consider the implication, right? As we know, this statement is always true if P is false, and otherwise it's true if Q is true, right? But what other formula expresses exactly this? Either P is false or Q is true. Okay? Now, let's use these laws to prove this. Okay? So how do we begin? Well, let's just negate the first statement, right? We'll add a not, okay? Now, we can use law 3. Now, we have not something and something else, right? Not class X and not good X. So we can use law 2, right? And here we can also use the law of double negation, right? Rather than writing not good X, we'll just write good X. And finally, we can now apply law 6. Okay, we have not class X or good X, which is equivalent to class X implies good X. And there's our proof. Here's our second statement. No man with long hair can fail to be a poet. And its negation, there is a man with long hair who is not a poet. Let's translate these into predicate logic. So the first statement, no man with long hair can fail to be a poet. So for any man X, say, if X is a man with long hair, right? So for any man X, if X has long hair, then he cannot fail to be a poet. So X is a poet, right? So for any X, okay, if X is hairy, let's say, we'll use this predicate to represent X has long hair. Then X cannot fail to be a poet, so X is a poet. And we'll use poet X to represent that. And the second statement, there is a man with long hair who is not a poet. Well, we can write that as exists X, right? There is some X such that X has long hair and X is not a poet. Yeah? So X has long hair and X is not a poet. We claim that the negation of this statement is this second statement. Let's show this using our laws of logic, right? So we'll begin by simply adding a not to the first statement to negate it. Now we can apply law 4. And we can apply law 6 to the implication, right? So we have hairy X implies poet X, and this is equivalent to not hairy X or poet X. Now we can apply law 1, right? We have negation of an or statement, and so we can equivalently write it as not hairy X and not poet X. And the not we can change to simply hairy X using the law of double negation. So let's write this. And this matches what we claimed originally. Here we have our third and final statement. Everyone who has not been vaccinated got sick. And its negation, there is someone who has not been vaccinated but did not get sick. So let's translate these two statements into predicate logic. Yeah? So first, everyone who has not been vaccinated got sick. Okay, so for any X, right? For any X, if X was not vaccinated, then X got sick, right? So for any person X, if X was not vaccinated, so not vaccinated, then X got sick. And the negation, there is someone who has not been vaccinated but did not get sick. So there exists some X, right? There exists some X such that X has not been vaccinated and X did not get sick. Let's prove this third and final claim using our laws of logic, right? So we start by negating the first statement by adding a not. Now, I'm going to first apply law 6 to the implication. So not vax X implies sick X. Sick X will become not vax X or sick X. Now the not vax X becomes vax X by the law of double negation. Now let's apply law 4. And finally, we can apply law 1. We have not vax x or sic x, which will become not vax x and not sic x. And that is as we claimed. Let's examine these lyrics taken from a song recorded by Doris Day. Everybody loves my baby, but my baby don't love nobody but me. If we use the predicate loves xy to represent the statement x loves y, we can easily express this first line in predicate logic. For any person x, x loves my baby. Everybody loves my baby. Let's try to express this second line. My baby don't love nobody but me. Another way to say this is for any person x, say, if my baby loves x, then x must be me, because my baby don't love nobody but me. Again, for any person x, if my baby loves x, then x equals me. Now let's see what we can deduce from these two statements. Firstly, any person x loves my baby. In particular, my baby loves my baby. So my baby loves my baby. But from the second statement, we can now deduce that since my baby loves my baby must in fact equal me. Which was perhaps not the original intention of the song. We want to formulate this expression in predicate logic. To do this, we'll use one predicate, name xn says that x's name is n. Now to say that every person whose name is Tom is named Sam, we can say that for any person x, say, if x's name is Tom, then x's name is Sam. Again, this says for any person x, if x's name is Tom, then x's name is Sam, or every Tom is named Sam. We can replace the name Tom here with Dick or Harry to express the statements every Dick is named Sam or every Harry is named Sam. And putting these three expressions together gives us every Tom, Dick and Harry is named Sam. We also want to express one more statement in predicate logic, and that is that every person has exactly one first name. Another way to say this is for any person x, if x's name is A and x's name is B, then A and B must in fact be equal. Again, this says for any person X, if X's name is A and X's name is B, then A and B are equal. A and B are the same name. And this expresses that every person has exactly one first name. Now, if your name is Tom, then by this first expression, your name is Sam. But since every person has exactly one first name, your name can't be Tom. And the same goes for the name Dick and the name Harry. So we can conclude that there are no Toms, Dicks, or Harrys. Consider this argument made by Lewis Carroll. Everybody who is sane can do logic. No lunatics are fit to serve on a jury. None of your sons can do logic. Therefore, none of your sons is fit to serve on a jury. We want to check if this is a valid argument, and predicate logic can help us out with this. So let's express each of the statements in predicate logic. First up, everybody who is sane can do logic. In other words, for any person X, say, if X is sane, then X can do logic. Again, this says for any person X, if X is sane, then X can do logic. The second premise is no lunatics are fit to serve on a jury. In other words, for any person X, if X is not sane, that is, if X is a lunatic, then X is not fit to serve on a jury. Thirdly, none of your sons can do logic. Or for any person X, if X is your son, then X cannot do logic. And the conclusion is that none of your sons is fit to serve on a jury. So if we translate that into predicate logic, it'll say for any person X, if X is your son, then X is not fit to serve on a jury. Now, premise 3 tells us that your sons cannot do logic. For any person X, if X is your son, then X cannot do logic. So your sons cannot do logic, and number 1 then tells us that your sons are not sane, since if they were sane, then they would be able to do logic. And then the second premise tells us that since your sons are not sane, they are not fit to serve on a jury. So your sons are not fit to serve on a jury, which is the conclusion we were looking for. So this is a valid argument. Consider these 3 statements. No professor is ignorant, all ignorant people are vain, and no professor is vain. Let's express these statements in predicate logic. First up, no professor is ignorant. In other words, for any person X, say, if X is a professor, then X is not ignorant. Secondly, all ignorant people are vain. In other words, for any person X, if X is ignorant, then X is vain. And lastly, the third statement, no professor is vain. We can express this as for any person X, if X is a professor, then X is not vain. Now, if we look at the third statement, this tells us that if you are a professor, then you are not vain. The second statement tells us that if you are not vain, then you must not be ignorant, since if you're ignorant, then you're vain. So putting these together tells us that if you are a professor, then you are not ignorant. That is, statement 1 follows from statements 2 and 3. What's wrong with this argument? A ham sandwich is better than nothing. Nothing is better than eternal happiness. Therefore, a ham sandwich is better than eternal happiness. The issue here is that the word nothing is being used differently in the two premises. To say that nothing is better than eternal happiness expresses that eternal happiness is the object with the highest value out of everything. To say that a ham sandwich is better than nothing simply expresses that a ham sandwich has some value. It doesn't make any comparisons between values of different objects, just says that a ham sandwich has some value. Now this is just a silly example, but it is ambiguities like these in natural English language that can lead to serious problems in real-life systems.